Hey, Charlie Pyatt here. For this project, I'm going to be revisiting the Statial adjustable mouse concept I did way back in 2013. Current competitive mouse grip styles have really grown out of players adapting their hands to the standardized shape of mice. I wanted to see if making a mouse with an adjustable shape results in new grip styles being invented that have better comfort, precision, and performance. I'm releasing the Statial as an open source project as well, so this video has two main sections. The first part covers the design process I went through in creating the Statial B, and the second part covers the assembly steps for making a mouse. Please check the link in my GitHub repository in the description for all the 3D print files, PCB files, and Arduino sketch if you want to build your own. The original concept of the Statial mouse was to combine a 3D printed part with an off-the-shelf product to make something new. By taking a low-cost Logitech M100 and adding a 3D printed hat, I could make an adjustable mouse with surfaces that could be moved then locked in place. The original Statial worked by having a center screw mechanism that would press two internal plates together. The plates would compress all the little internal hinges and lock off all the surfaces. This original design had some downsides though. The various surfaces were movable on a flat plane, but they couldn't be adjusted vertically or have any pitch or roll. Another issue was that I had to use a cheap off-the-shelf mouse to drive everything. More expensive, higher-margin mouse designs tend to change every year or so. I didn't want to redesign the Statial every 12 months, so I had to pick a lower-cost product to base everything off of. The Logitech M100 fit that bill really nicely and still has the same footprint over a decade later. Unfortunately, this mouse uses a pretty dated sensor though, which makes it not really usable for gaming and precision applications. With this new version of the Statial, I wanted to fix some of the shortcomings of the old design. I'm still going to stick with the same basic adjustable surface breakup I used in the original, so we'll have movable left-right buttons, left-right surface, and rear. I want all these surfaces to be fully adjustable up, down, left, right, as well as to be able to pitch forward and back and roll left and right. Because of all the axis of freedom I want to include, I'm going to ditch the center locking mechanism. If I tried to keep that, the mechanics would get way too complicated and there would be too much slop in the locking system. I'm also going to switch from an off-the-shelf mouse to a custom-assembled subcomponent setup. These boards will have a much smaller form factor than using off-the-shelf mouse internals and should also help keep the costs down on the project. Before I move on to any creative or engineering work, I like to do some research to see how the market has changed. I feel like the mouse industry has moved more into improved sensor resolutions and some specialized weight reduction designs. The overall ergonomic development in this space seems really unchanged as far as I can see. The shape of a performance mouse today is very similar to what it was a decade ago. This stagnation is actually pretty surprising to me. There's been an explosion in custom and specialized split keyboards over the last several years, but that really hasn't carried over to the performance mouse space for some reason. In any case, it seems like a really great time to step back into the ergonomic mouse space and see about pushing things forward a little bit. I'm going to start the actual design side of things off by exploring my mechanical engineering constraints for the new Statial B. My first step is going to be to 3D scan in a standard mouse form. For this, I'm going to use a Razer DeathAdder Elite, which has been my default go-to productivity mouse for years now. It also has a relatively standardized form factor, so it'll be a good baseline size reference to use going forward. With my reference mouse scanned in, I'm going to model some surfaces in place in Rhino 3D. These are just going to be rough placeholders for the parts that'll be movable in the final design. From here, I need to establish the range of motion I'm going to want for each surface. For this, I created a grasshopper script in Rhino. I'm basically just drawing in these color-coded spheres and then measuring the angle and distance changes between all the surfaces I move around. Once I have everything in position for the claw, palm, and finger grip types, I can check the range of motion I need out of my surfaces. So after I have all this set up, I'm already starting to see some interesting results. The front buttons and mouse wheel are all similar lengths regardless of what grip type they're set to. That means I think I can get away with just putting these elements all on fixed length arms and connecting them to ball joints on either end. The left side, right side, and rear surfaces will need to be a little bit more complicated. These will also need to be arms on ball joints, just like the front buttons, but also need to be able to be extended in and out to cover a range of motions I'm looking for. Now that I have a basic idea of my mechanical requirements, I want to take a second to figure out my electronics components. For this design, I'm going to stick with making a wired mouse. As for my electronics, the Ben Makes Everything mouse project and Daniel Cow's trackball mouse build were pretty important sources for what I was trying to do. I'm going to use the same sensor and controller combo used in those projects in the PixArt PMW3389 optical sensor and the Pro Micro. Plan on making my mouse have pretty similar capabilities as other performance mice, with left-right mouse buttons, middle mouse buttons, scroll wheel, and forward and back buttons. I can wire all my switches and rotary encoders into the Pro Micro through plugs or connectors of some kind and be good to go. Once I had everything in, I plugged in all the components into a breadboard and tested out the setup. I made some quick modifications to the Arduino codebase, but everything worked out pretty well from the get-go. I was originally thinking of just direct soldering the PMW sensor to the Pro Micro, but realized it would take up too much space inside the mouse if I went that route. Instead, I decided to design a custom PCB to connect the two boards. Problem with all this is last time I fabricated a PCB, it involved faxing away to Radio Shack to get an acid etching kit from a catalog. That's just about the oldest sentence it's possible to say. For my PCB design, I used KiCad and got up to speed watching a bunch of tutorials. I planned on just doing a basic through-hole bridge board with sensor on one side and the Pro Micro on the other, but almost immediately ran into issues with the layout. If I centered both the Pro Micro and sensor over each other, their pins would hit. I couldn't put them side by side on the board because of space constraints, so I ran them vertically on the bridge board design and hoped for the best. After that, I output the Gerber files from KiCad and sent the first round PCB design off to be fabricated. My first round of PCBs came back looking great, so I soldered them up. When I plugged in the Pro Micro, the sensor came right on and everything worked. The problem was, the more I looked at it, the board and DuPont connectors were just going to be too large to fit inside the available area in the mouse. Having the sensor and Pro Micro offset vertically was taking up too much space. I started browsing ways of connecting the boards that would allow them to be mounted on top of each other and also keep them in a much lower profile. What I eventually discovered was a surface mount gullwing headers. These would allow me to make the entire package far more compact and were perfect for my application. For plugging the buttons into the board, I also looked at a bunch of different connectors and port options. I eventually landed on PH-style connectors. These are pretty robust and compact and are commonly used for connecting batteries to PCBs and electronics. Downside is these little guys are super annoying to crimp. Kept looking for other options, but these really were the best solution for the use case, so I bit the bullet and committed to using them. On the bright side, the right-angle versions of the PH connectors are also easy enough to find, and that will help even more with compacting my layout into a smaller space. With all that decided, I output another Gerber file and sent the new PCB away to be fabricated. Designing and testing the printed circuit boards for the Statial took a lot of work over the course of several weeks. After researching a bunch of manufacturing options, I settled on using JLCPCB for my electronics fabrication. To be honest, I was a little intimidated about ordering my first set of boards, but the costs were so low and the turnaround was so quick, I really didn't have to worry about making mistakes. Later on, while I was working on the edit for this video, I was super surprised to have JLCPCB reach out offering to sponsor this project. Because I was already really happy with how simple it was to order, the quality results, and fast delivery, it was an easy thing to agree to. JLCPCB offers 1 to 8 layer PCBs starting at $2 and lead times as fast as 24 hours with strict quality control that's trusted by 5.4 million customers worldwide. JLCPCB's Engineers Day is also going on right now from September 5th through October 5th, 2024, offering up to $125 off coupons, bulk order discounts, and a chance to win a $150 Amazon gift card. So if you want an extra discount on ordering the custom PCBs for building your own Statial mouse, now is a great time to do it. Use the link in the description below to check out JLCPCB's Engineers Day. As I've been waiting for my electronics components to come in, I've been modeling and printing out test ball joints and extension arms. Because I'm going to propagate the same arms and ball joints throughout the design, I really need to make sure I have those totally figured out and thoroughly tested before going on. The idea with all these was pretty similar. I would have some kind of ball joint that would seat into a socket. The socket would then have a set screw that would tighten down and lock the ball joint into position. Likewise, the extension arm would use some kind of metal tube or pipe and have a set screw that would lock it in place. I eventually ended up with a complete ball joint receiver design, static arm, and extension arm variation. Next step was to integrate these parts into my design and start building around them. I already knew approximately where these needed to go in 3D space from the earlier Rhino Grasshopper exercise, so I just imported that source file into Fusion to use as a reference for my CAD work. In this case, I ended up drawing a 3D driver sketch that would position all my various ball joints. Then I could import these positioned ball joints into a new part and start building around it. As I moved through my mechanical CAD work, I started putting together a style board for the project. This is just a collection of images and reference pictures for the styling of the product. In a normal commercial project on an industrial design team, you would usually do the styling first and then refine design concepts that would get sent over to the engineering team to implement last. In this case, the mechanical engineering is so integral to the design that I'm doing that first and the styling absurdly late in the process. I actually find this to be a better way to work in many projects because it makes it so the mechanics and styling are playing off each other, creating a more unified and interesting product. As I worked through the mechanics, I started to see some reoccurring forms that I really like and wanted to lean further into. The front buttons had a very vinyl records stylus vibe to them, with the mouse switches looking like the cartridge, which I really liked. I decided to use the mouse feet or glides off a Logitech G Pro for my new design, which is a head nod to the first Statial concept that used a Logitech M100 base. I was also seeing some KUKA arm styling coming out in some of the extension arm details. Some of the custom split keyboard images are great because they have exposed components like I'm going to end up with in the Statial B. This mood board was something I would keep returning to through the build to add or take images out of. I use it as kind of like a scrapbook to help keep a coherent design sense of style through the whole project as I work through the development. Back in Fusion, I'm going to keep refining all of my parts. You can see on the front button I took in that record stylus look and tried to capture that feeling. Functionally, the actual top button surface will flex down and a little hammer here will hit that switch. Center area will hold the electronics package and all the ports to plug my buttons into. I've imported the new electronic assembly from KiCad and started my build around it. After that, I'm bringing in the ball joint parts from my master sketch and building connections between everything. Split the lower base that encloses the electronics and added a shadow gap to hide the seam between the upper and lower parts. This is kind of a classic move to hide imperfections when you're assembling parts together. After that, I moved to the left side. This is the right-handed version of the mouse, so the front and back thumb switches are going to be on the left side. I created these on flex arms similar to the front buttons. That'll let me print this side surface in fewer parts and not have to worry about independently capturing those buttons. As I work on everything, I'm going back to the master assembly and making sure all the parts are still falling inside that original reference scan I did. I want to make sure the Statial fits inside there when it's in its tiniest form. After that, I'm moving over to the rear surface. For this one, I have to start making sure that my exterior moving parts aren't covering the ball joint screws. There always has to be a way to access those screws so I can unlock the surfaces. For the rear surface especially, this involves cutting out a bunch of notches and holes in the design for this to work. The final area of the mouse that I've been putting off is the center wheel area. This is a super complicated component that has the rotary encoder for the mouse, the DPI adjustment button, and the middle mouse button. Managing all the part clearances in this one is really brutal. I'd make a little change to the wheel and it would bind, or the button hammer would miss, or the resistance would be too high, or the assembly would be too complicated, or any other one of 100 problems would happen. I managed to finally get it together though in a complete package. I actually really like how the mouse switch ended up sticking out the front of this and being super visible. It's a really unique and funky look with all the electronics components partially exposed that I really like. With the first version of the mouse done in Fusion, I'm going to output some of the parts to do post-processing in Rhino and Grasshopper. There's a select few parts that are going to have holes cut out of them, and then the subtracted areas are going to be filled with lattice geometry. This will help reduce weight and the amount of resin used in the printing process. It'll also make the lighting effects visible and just make the whole thing a lot more interesting as a product. I went into more detail on the lattice process in my last video on the custom VR mask. If you're interested in the lattice generation process, please check out that video for more details. The Grasshopper file takes in the output geometry from Fusion and rebuilds all these lattice details into the surfaces. Now that I have my final surfaces with the lattice treatment done, I can finally save out these finished parts and I have my complete print set ready to go. With all my first round of parts saved out and ready to print, I'm going to move on to setting up the parts in my slicer. For printing, I'm going to be using a Form 4 printer with a range of different resins. I usually use a clear for the first round of testing so I can see through my design and tell where parts are hitting or causing problems. I'm going to do my final in Tough 2000, which is a really durable and versatile resin for final parts like this. I did some other testing using Anycubic's ABS-like Pro 2 resins and had good results as well. With everything set up, I can run my prints and take them through post-processing in an IPA bath and final UV curing. My first round assembly is going to need a lot of changes, which isn't a surprise. All that said, the adjustments and general layout of everything was working really well. I had to do about 5 rounds of prints before I was able to get my final design wrapped up. I'd already built out my final electronics components, so I was able to just migrate those into each new build as I went. With all that done, I had my complete design revisions and was ready for a final finished product assembly. This is going to be my first publicly released project on the channel. Print files, bill of materials, and assembly instructions are all available on my Statial B GitHub repository if you want to build this project yourself. Statial is a working prototype designed to explore mouse ergonomics. That means it's more finicky and fragile than a normal mouse, and that's just part of the nature of prototype builds like this. This is also a relatively complicated project to build. You'll need basic knowledge of 3D printing, soldering, and some basics of working with Arduinos. Total build price for this project is a little under $200 US in mid-2024 money. That doesn't include the price of a resin printer and miscellaneous tools. Finally, this is a heavy little guy. Most of the performance mice out there are going to come in at under 100 grams. The Statial, on the other hand, is 130 grams total, depending on the hardware used. And this isn't outside the norms of popular gaming mice out there, but if you're looking for an ultralight mouse solution, this just isn't it. All that said, the Statial works great. There's really nothing else like it out there if you're looking to explore mouse ergonomics. I used the first Statial B model to build all the subsequent prototypes, and the final version to do all the editing for this video. It's been a blast to use over the last bunch of weeks. The adjustability is beyond anything else you can find, and I really like changing the layout whenever I feel like it. In any case, with all that out of the way, let's get on to the final build. First thing you're going to need to do is go to the GitHub repository for the project and download the print files, Arduino sketch, and instructions PDF. The PDF has a complete list of parts you'll need to order in the BOM. Most of the hardware and electronic parts are pretty generic. The only specialized parts are going to be found in the PMW 3389 sensor board and the custom bridge PCB. For all the other components, I would recommend looking around and finding things for as cheap as possible in bundled kits and packages. Point is, there's money to be saved if you're on a budget on this build. To order the PCB, you're going to want to go back to the GitHub repository and select the Gerber directory. Inside this, you can select the Gerber zip file and click the Download Raw Data in the upper right. This will save the Gerber file to your local computer. After that, go to JLCPCB and upload the Gerber file. You can leave most of these settings at default. The only important one you want to change is the number of designs set to 2. I also switched my board color to blue just because I like that color better, but that's just personal preference. From that, you can just complete your order and your board should be on the way. Once you have all the parts, you can move on to the 3D printing. I included preform and Lattice files ready for printing in the GitHub repo. These are print files for the right-handed version. If you want to make the Statial B for left-handed use, you'll need to download the alternate parts in the extras folder. If you need to use a different slicer or build layout, then you can just download the STL files and set them up for any 3D resin printer you have access to. Once you have all the electronics, hardware, and 3D printed parts together, you should be good to start the build. First step is going to be to separate the custom PCBs. These come as a family board with pre-scored connections that you can just snap apart. From there, you can clean up the edges with a piece of sandpaper or a nail file. Next up, I'm going to trim down my surface mount gull wing headers. These usually come in 40-pin lengths that you can just cut with a pair of wire cutters. Because these are surface mount pins, you won't have the benefit of through holes to help with alignment. It's really easy to start soldering these from one end, and by the time you get to the other, they've drifted to the left or right. I found the easiest workaround for this was just to solder the first pin and the last pin, and then do all the in-between ones. So you're just going to do the 2 sets of 12 for the Pro Micro on one side, and the single strip of 8 on the other. With that done, I'm going to start soldering on my JST-PH connectors. These are right angle sockets that I'll be plugging all my external buttons into. From there, I'm going to solder on my NeoPixel. This is a surface mount LED, but I'm going to be using a little run of wire to push it off that main board. For more information on the wiring, you can check my instruction PDF on the GitHub repository for this project. The final step in the electronics assembly is to solder on the ProMicro and PMW3389 optical sensor. It's really important to solder these boards on last because they will cover up a bunch of the soldering points for the other components. I would also recommend plugging in the ProMicro and testing it out before getting to this step. Sometimes the clone ProMicro boards can have some quality assurance issues, and you want to make sure you don't have a dud before you solder this all in place. With that done, you can solder the optical sensor onto the back of the custom PCB. Just want to make sure the optical sensor is facing away from the main board like it's shown here. With that done, you can plug it in and give it a test. Assuming everything's working okay, you can trim off the end of those header pins. With that, the main electronics assembly is all wrapped up. The Statial B uses a micro USB cable to connect it to the computer. There are basically two options for setting this up. You can use a normal off-the-shelf micro USB cable and just remove the sheathing on the last 85mm or so of the cable. The drawback of this option is most micro USB cables are actually pretty thick and unflexible. This adds resistance when you're trying to move the mouse around. The second option is to modify a normal mouse cable. If you go this route, you're basically going to be trimming off the cable's existing connector and soldering on a new micro USB one. This takes a little bit more effort, but you'll end up with a much more flexible and versatile cable in the end. Last step here is to plug in the micro USB and secure the NeoPixel LED with a dab of hot glue or double stick tape. I'm going to plug the electronics assembly in and make sure everything's still working. As I go through each of these steps, I'm periodically plugging in the components. That way I know if there's a failure of some sort, it's the most recent thing I installed that's causing the problem. But yeah, this is great. You can see the NeoPixels running and the tracking is all working fine. I'm basically doing this assembly from the inside out. So now that the innermost electronics components are all done, I can move on to assembling the 3D printed parts. I'm going to start with the top of the inner mouse body. First step here is just to load these M2 nuts into the slots in this top part. After that, I'm going to be doing the ball joint locks. This is a reoccurring assembly part that'll be done over and over again throughout the model. These take an M2.5 nuts and a M2.5 set screw. When you tighten the set screw, it'll push down on a tab and lock the ball joint up. Right now I'm leaving these relatively loose, and in later steps, once I get the ball joint arms in there, I can tighten them down further. With the top inner body done, I'm going to move on to the bottom part. For this, I'm going to attach my mouse glides. These are third-party glides for a Logitech G Pro. I'm just pushing down on the adhesive back and securing them in place. Next up, I'm going to seat the electronics assembly in place. For this, I just have to make sure the plastic lens is on correctly and that lens seats into its registration okay. After that, I can press that inner body top on and screw in the 16mm M2 screws to lock everything down. Now that the assembly of the inner core of the Statial B is done, I'm going to move on to the arm assembly. There are 4 of these adjustable length arms. These have 1/8 inch diameter aluminum tube stock in the middle and are capped with 3D prints on either end. There are a couple set screws that can be released to adjust the lengths of those arms. Loading M2 nuts into the ball joints at the end and tightening them down. This will lock those aluminum tubes in place. After I slide those on and tighten everything down, I have my set of 4 adjustable arms ready to go. From there, I'm going to be snapping those ball joints into the sockets. This can range from being super easy to being really difficult depending on the 3D printer and resin used. If it was really resisting going in, I would just use a pair of pliers to snap them in place. To start off my outside assembly, I'm going to begin by putting together the left and right mouse buttons. First thing I'm going to do here is trim off these extra supports. These are left in during post-curing of these parts to make sure they don't warp out of shape. I'm also going to be wiring up those mouse switches. I'm just direct soldering to the center post and the post on the switch side. Then I have to wire up my JLCPCB connectors on the other end. As I mentioned, these things are a real pain in the butt to get on, but after enough practice, you get pretty good at it. For this, I'm going to be using this PA09 crimping tool, and I'm going to be doing 2 crimps. One crimp goes over the wire, and the other goes over the wire sheathing. After that, you press them into the pH connector and you're all done. Back on the button itself, I'm dropping in an M2 nut and an M2 button head screw. This screw will keep the mouse switch retained in its little channel. I'm going to test the mouse and make sure it's all nice and clicky. And then I'm also going to use a multimeter just to make sure it's activating the switch. From there, I just repeat the process for the other side, and I have my left and right mouse buttons all wrapped up. So we're finally on to the middle mouse button assembly. This is by far the most difficult part of the entire assembly process for the Statial B. There's just a lot of electronics and components that all have to come together in a specific order to get right. To begin, you're going to want to cut down 120 millimeters of 5 conductor 28 gauge ribbon wire. You're going to do the same process as the left and right mouse buttons and crimp the ends of the wires to seat into the 5-port pH connector. With the connector on the wire, we're going to be soldering it into the mini PCB. This is the other smaller breakaway board that we separated from the main PCB earlier on. There's a more complete wiring diagram in the instructions PDF, which I really recommend looking up before doing this. Once the 5-wire connector is soldered into the board, we can move on to the rotary encoder. The rotary encoder wire should be about 30 millimeters long to clear its way into the middle mouse button assembly. Next up, solder a run of wire into the DPI switch on the left and the middle mouse button on the right. Now we're going to start integrating those components into the 3D printed parts. You can seat the rotary encoder into the encoder cap. I want to do a dab of lithium grease in there too, just to make sure you're getting a smooth roller motion in the wheel. And then push that assembly onto the 3D printed wheel. From there you can push that whole part onto the flex frame. This rotary encoder assembly will deflect down and hit the middle mouse button. Final step is to hook that flex frame down over the cradle and secure it in place with the DPI cap. Once this is all done, the wheel should scroll smoothly and you should get a nice clicking motion hitting that mouse switch when you press down. I'd highly recommend plugging this into the Statial B at this point and just testing it to make sure you're getting a good scroll wheel, mouse button, and DPI switch. It's a lot easier to fix any wiring problems at this point than it is after the full assembly. The last bit of wiring is on the thumb side surface. This side carries the forward and backward mouse buttons. For this build, I'm doing a righty version of the Statial B. If you're left-handed, you can download a mirrored version of this part off my GitHub repository under the extras folder. Otherwise, the assembly process is exactly the same for the lefty and righty versions. For wiring up the switches in the thumb side surface, I'm going to cut a 3-wire length of 28 gauge wire. These switches are a shared ground, so I'm going to splice in a Y connection at the center and then connect those outside wires to the middle posts of the switches themselves. After that, I'm going to go back to the good old crimping of the pH connectors, and I should have this electronics wiring assembly done. These switches fit into a pocket in that side surface there. After that, an M2 nut is loaded into the slot, and a button head screw secures the upper switch bracket. Now that I have all my subcomponents assembled, it's time for the final surface assembly onto the core of the Statial B. The order of the steps from here on out doesn't really matter. I usually start with the front, left, right, and middle mouse button assemblies and move back from there. You're just basically popping these on to their matching ball sockets. Sometimes these sockets can be pretty sticky and may require a gentle use of pliers to get them in place. After attaching each surface, you can plug in its matching port. Front, left, and right buttons are at the front, left, and right of the core. The middle mouse button snakes back to the right rear, and the forward backward thumb buttons plug in on the left side of the Statial B. But yeah, from there you just adjust all the surfaces to your liking and tighten everything down. Plug it in for a final test and you should be good to go. All the ball joints are unlocked by using a 1.3mm hex wrench. This wrench can be stored in a bracket on the underside of the Statial B. All you have to do is simply loosen the set screw in the ball socket you want to adjust and move the surface. The front arms are asymmetrical and can be rotated around. When they're in their inverted position, they'll extend the mouse buttons up significantly higher than when they're in their normal down position. Just be careful when you're rotating these or moving any other surface that you're not putting too much tension on any of the connection wires for those buttons. The DPI toggle is a small button behind the scroll wheel. Pressing this cycles through a bunch of DPI presets and changes the LED color for each preset. These presets and LED behaviors can all be changed in the Arduino IDE for this project. All the buttons on the Statial are standard by default, but like the DPI presets, you can change the buttons to different key assignments if you like. Final thing I wanted to cover is the common configurations for the Statial. In general, it's much easier to make a super uncomfortable mouse than a good one with the Statial. The first instinct with something like this is to go crazy and extend the surfaces all out in different directions. This will result in a super arthritic-inducing situation you probably want to avoid. I'd recommend setting the surfaces as close to a regular mouse position as possible, then making slow micro adjustments as you use the Statial. It's amazing the impact a 1mm or 1 degree position change can do to the ergonomics of a mouse, and it's important to think about things in that scale as you make changes. With the palm grip, your index finger M1 button is the highest, and there's a downward angle into your M2 button. If you look at a normal mouse, you can see this angle is actually pretty severe. Your thumb should rest comfortably in between the front and back buttons on the left side surface, and your pinky should have good surface contact on the right side of the mouse. The back of the mouse should rest securely against your palm, but not be under any serious pressure when your fingers are in position on the front buttons. For the claw grip, you can look into moving the back surface up and forward to compress your grip on the buttons. I've been messing around with pitching the front buttons forward to see how that affects playstyle. With this pitched forward layout, you can have a much more natural pull-in motion whenever you click. I'm not a claw grip player myself, so I'd be interested in hearing if people find this better or worse than a normal mouse. The finger grip is pretty fun with the Statial. You can aggressively tilt the left and right surfaces to match the angles of your fingers and mess around with extending the rear of the mouse way up. You can also fully remove the rear of the Statial entirely for a backless mouse to save some weight and get an even weirder layout. Final category is the vertical. As I'm getting older, I'm leaning more towards a comfortable hand position over a performance grip. I've tried vertical mice in the past and always end up ditching them because they feel so clunky and imprecise for moving the cursor. With the Statial, you can get a really nice half vertical layout, I guess I'd call it. It's a really unique setup, and for me at least, it's super comfortable to use. These are really just some basic options for setting up the most common grip styles out there, and there's an infinite number of variations on these layouts to be explored. I'm really into physically adjustable products as a concept, so it's been super fun revisiting this design. Since I did the original Statial over a decade ago, I've had all these updates rattling around in my head, and it's just been great to get a chance to finally put them out into the world. Beyond that, I hope there's some interest in building a Statial for yourself. Please hit the link in the description to visit my GitHub repository for 3D print files, PC fabrication files, and complete instructions. Thanks for watching, and see you next time.